All right, let's take a look at some problems from the extra practice pages in the back of the textbook. The page number is EP2 and EP3 for Chapter 1. As you're watching the video, I'll be using various problems throughout. Make sure if it's one that you can pause the video and work out first, go ahead and do that, and then come back and make sure that you had the correct answer from the explanation that was given. Let's take a look at number 1. In this diagram, it says, name 3 points that are collinear, and then give a name for the line that contains the points. Well, we have 2 different options this time. We can take point A, point F, and point B. Again, collinear means on the same line. These 3 points are all shown to be on that same line, and we can write line AB is one way of writing that line. We could write line AF, or we could write line FB, and that's one way of doing it. Now, if we reverse the order of the letters on those, BA, FA, BF, we still have the exact same line. Well, that's 3 ways of naming that one line. Let's take a look at another possibility of 3 points that are collinear. Let's look at this point E, point F, and point G. Line EG is going through the plane. It hits this plane at point F. So we can name the line as EG, or we can say EF, or we could say FG. Any of those 3 ways are naming the same line. The point of intersection with this line and the plane is point F. And this is like what we talked about when you have a sandwich and a toothpick goes through it. The toothpick is the line intersecting the plane, which is the piece of bread for the surface, and F is where it hits. All right, let's take a look at number 2. Name the intersection of plane ABC and line EG. Well, here we have the line EG, and let's go over it. Here's the part that you can see above, all right, and this dashed part right there is what's underneath the plane and then coming out on the other side, all right? So, as we said previously, this line EG is intersecting plane ABC at point F, all right? So this is the point of intersection of that line and that plane. Let's take a look at number 3. Number 3 says, name 2 pairs of opposite rays. Well, opposite rays are 2 rays that form a line from a given point. They have to have the same starting point. So I'm going to look at point F, and I'm going to go through point B. So I have ray FB. Again, you start from the left, you go to the right. Now, what ray is going to be opposite to that? It has to be the opposite direction from the same starting point. That's going to be coming this direction. So, ray FA. Again, notice they have the same starting point and they are opposite rays. Well, that's one way of naming a pair of opposite rays. Let's try another way. And again, we'll start with point F. If we go up on this line, EG, through point E, well, we have ray FE, but we could also go in the opposite direction, going down through G, and so ray FE and FG, these are opposite rays. They form a line, and again, notice their starting point is exactly the same. Opposite rays always start from the same point. Well, let's go on to question number 4. It says, are the points A, C, and G coplanar? Right? Then it asks for an explanation. Well, let's take a look at A, C, and G. A, C, G. Now, the question is asking, are they coplanar? It's not asking, are they in this plane ABC, the blue one that's pictured? And that's the reason why most people would miss this, is because they would say, no, G is not in the same plane as A and C. It's not in the blue plane. However, we have a theorem or a postulate that says between any 3 non-collinear points, there is exactly one plane. And so there is a plane. If we connect A, C, and G, this is a triangular section of that plane. That plane would actually exist because it's 3 non-collinear points. Again, there is a plane, it's just not the one that's shown in blue. Okay? So that's a tricky one. Let's take a look at number 5. Let me erase this. It says, name a line that intersects plane AFD at more than 1 point. All right, so AFD. Well, again, D is in the plane ACB. So name a line that intersects that plane and more than 1 point. Well, we could have this line AB. Now, why would AB intersect at more than 1 point? Well, you can see F is right here as well. All right, that plane has an infinite number of points. We're looking at 3 of them, A, F, and B. And because plane AFD is the blue plane, well, this line AB is in that plane. So it's intersecting every point on the line with that point in the plane. That's one way of labeling it. Let's find another one. Here is line FC. Line FC is in the plane. And so because it's in the plane, it is intersecting that plane at every point that exists in that line. The other one then would be line AC. And so this would be our third option from the lines that are shown. There are a lot of other lines that could be. We could go from C to B and maybe A through D, B through D. We could pick lines that aren't shown, but we just have to name one that is. All right? Let's continue on to problems 6 through 11. Let's take a couple of these. It says, in the diagram, P, Q, R, S, and T are collinear. Again, collinear means in the same line. And then it says that the length of PT is 54. The length of QT is 42. The length of QS is 31. And the length of RS is 17. Find the indicated lengths. Well, the first thing that I want to do is go through and label as much information as I can. And I'm going to start with that last piece. RS is equal to 17. That's one segment from R to S. It's not going multiple segments. And now I'm going to start backing up. QS is 31. Well, let's take it. If QS is equal to 31, and we know that RS is 17, well, the segment addition postulate says that QR plus RS has got to equal this 31. So what does the length of QR have to be? That's 14 from here to here. So the length of QR is 14. Writing that down. Well, I'm going to back up one more. It says that the length of Q to T is 42. So from Q all the way to T out here, this has got to be 42. Well, we already know that from Q to S is 31, so how much more is needed to get to 42? Well, that would be 11. Now look at this. From Q to T, all the way from here to T, that's 14 plus 17 plus 11, and so that is 42. So we now know that the length of ST has to be 11 units. And then finally, the very first piece of information that we had, PT was equal to 54. Well, if we know that PT all the way from here to T is 54, and we know that Q to T is 42, what does that leave for this segment from P to Q? Well, again, segment addition postulate says these two segments have to add up to equal that amount. So 42 plus 12. So I'm going to put down P, Q is equal to 12. And now I'm going to go through and start answering the questions. And notice that I'm answering the questions after I've labeled as much information as I possibly can. Number 6, the length of PQ, 12. Number 7, the length of P to S. Well, PS is going to equal PQ plus QR plus RS. It's going from P all the way to S. So the 12 plus the 14 and the 17, those are the individual segment lengths. Well, 12 plus 14 is 26 plus another 17. That's 43 units. Let's take a look at number 8, Q to R. Again, number 8 we answered a while ago without knowing it. QR is 14. Number 9, P to R. Well, for 9, PR is equal to PQ plus QR. Again, 12 plus 14, that's 26 units. Number 10, we've already answered. Segment ST has a length of 11. And then finally, number 11 says RT. Well, again, for RT, that's made up of the segments RS plus ST. RS we know is 17. ST we figured out was 11. And so this is 28. All right? So again, if you have a problem like this, where you have a line segment given and they're asking for individual pieces, put down as much information as you can first, and then go through and answer the questions that are there. Let's take a look at example 12. It says point B is between A and C on segment AC. Use this given information to write an equation in terms of X, and then solve the equation. Then find the lengths of both AB and BC and determine whether those two segments are congruent. Well, it says that B is between A and C, so I'm just going to draw a segment, make my endpoints be A and C. And now for B, I don't want to put it in the middle because that makes me think that it has to be a midpoint. This doesn't say that it's a midpoint. So I'm just going to put B over here on the left side. Doesn't matter where. But now then, I can go through and label each of these segments. AB is x plus 3. BC is 2x plus 1. And the entire length, AC, is 10. So what's an equation that we could write down? Well, again, segment addition postulate says x plus 3, the length of AB, plus 2x plus 1, the length of BC, has to equal the entire length of AC, which is 10. Right? Well, now we've got some algebra. We need to simplify on the left-hand side. The x plus 2x adds up to 3x. The 3 plus 1, again, combining like terms, plus 4 is equal to 10. Let's move the 4 on the other side by subtracting. So 3x is equal to 6. And then finally, dividing both sides by 3, x is equal to 2. They asked us to solve the equation. We've done that. We've also got to find the length of AB. Well, AB is x plus 3, so plugging in the 2 plus 3, that's 5, the length of AB. Well, we also need to find the length of BC. So, plugging in 2 here. 2 times 2 is 4, plus 1, and that is 5. Now then, it says determine whether those two segments, AB and BC, are congruent. Well, they both have the exact same measure of 5. So AB is congruent with BC, which means that in this particular case, B is the midpoint, right? So we didn't start with B having to be the midpoint, but we found out that in this particular example, it is the midpoint. Let's take a look at another one. Again, we have to start with the same setup. So I'll copy, draw this line down A to C. And again, I'm going to put B somewhere in between, but I'm not going to put it in the middle. This time I'll put it over here towards the right. And again, label the lengths. The length of AB is 3x minus 7. The length of BC is 2x plus 5. And the entire length of A to C is 108. Well, the equation that we need to write down is AB, 3x minus 7, plus BC, 2x plus 5, is equal to the entire length AC, which is 108. Again, combining like terms, the 3x and the 2x, those are like terms, they add up to 5x. Minus 7 and the plus 5, it's going to be minus 2. That's equal to 108. Adding 2 to both sides, we have 5x is equal to 110. And then to eliminate the 5, we divide both sides by 5. X is equal to 22. Well, now that we know the length for x, the value for x, we can substitute it back in. So 3 times 22, this is going to be 66 minus 7, which is 59. Well, the other one is 2 times 22, which is 44, plus 5, and 44 plus 5 is 49. So we found the lengths of both AB and BC. Are they congruent? No. The length of one is 59, the length of the other is 49. So the two segments are not congruent. B is not a midpoint. So again, don't make the mistake of putting it right in the middle when it says between, because it may not be the midpoint, and that makes you think that it is. Let's go on to Problem 21 says find the coordinates of the midpoint of the segment with the given endpoints. All right. Well, if you have both of the endpoints, the way that I like to do it is to go ahead and use the midpoint formula. Well, the midpoint formula is the average of the x coordinates. That's x1 plus x2 divided by 2. That's the average. And then also for the y coordinates, you take their average, which is adding them together, dividing by 2. So, plugging in, my x1 is 3. That's from the first point coordinate, plus it's a -1 for x2. Well, we don't put plus minus, so we just put -1 divided by 2. And then for the y values, y1 is a -7 plus y2 is 9, again divided by 2. And now we need to simplify. 3 minus 1 is 2 over 2. And -7 plus 9 is also 2 over 2. But again, what is 2 divided by 2 in each of these cases? This is a 1, and this is also 1. So the midpoint between G and H is 1, 1. Now, that's one way that a question could be asked. A way that is not asked in the extra practice here that we're going to do anyway is, what if you have a point that's given and you have the midpoint that's given and they want the other endpoint? This is what I want to look at now. So let's forget this and just take a couple of points. All right, I'm going to say some point A is, say, 3, -8. And a midpoint is known. And let's say that it's -2, 5. What is another endpoint B? Well, we've got the midpoint. And on this one, all that I do is I look, 3 plus what gives me a -2? Well, it's not a plus because we're going down. How far down do you go from 3 to -2? You go down 5. So I'm putting the -5 between them, but also on the other side, between M and B, I also have to go -5 in the x direction because it's a midpoint. I have to go the exact same distance. -2 minus 5, that's a -7. Well, let's go to the y coordinates. -8 plus what equals 5? Well, -8's on the left side of 0, so we have to go 8 units to get to 0 plus another 5. That's plus 13. Well, if I'm moving positive 13, I also have to add 13 on the other side. So 5 plus 13, 18. Anytime that you see a problem where the midpoint is given and one of the two endpoints, this is a much faster method instead of plugging directly into the midpoint formula. For me, that's a whole lot harder. So I'll try that. Let's keep going. Let's take a look at number 30. It says, use the given information to find the indicated angle measure. Well, QPS is this entire angle here that I'm marking out in green. It's the whole angle. Well, this is the angle addition postulate. Angle QPS is made up of these two angles, 57 and 64. All we have to do to get the entire angle is add them together. So 57 and 64, that turns out to be 121 degrees. And this is all we have to do for number 30. Let's take a look at number 32. Now in this diagram, we see some different information. Notice in number 30, let's just go back to it. These two angles, 57 and 64, they are not the same angle. But on 32, these arcs in red show us that this angle here, angle YWZ, has exactly the same measure as XWY because of the arcs that are here. So if these two are the same, then this also has to be 43 degrees. Well, if that's 43 degrees, then this ray WY is an angle bisector. It just happens to be, this time, an angle bisector. Why? Because the two angles that are there are both the same, 43 and 43. So what's the measure of angle XWZ? We're just adding these two together. We want the whole thing. That has to be 86 degrees. All right, let's take a look at 33. This time, it says the entire angle ABC, its measure is 133 degrees. And now then it says find the measure of angle ABD. This angle down here is the one that it's asking for, the one that I'm outlining in green. Well, we have to start with the initial information and say that the measure of angle ABC, it's these two angles, this one and this one. Those look to be different, right? They're definitely not the same. So you don't set 3x plus 9 equal to 7x plus 4. It does not say that ray BD is an angle bisector. So we need to write down 7x plus 4 plus 3x plus 9 is equal to 133 degrees. Now once we have this, again, we go back to the algebra. Combine the like terms. We have x's here, 7x and 3x. That's 10x. We have numbers that we can combine. The 4 and the 9, those add up to 13, and this is equal to 133. Now then, we need to get the x term by itself, so let's subtract 13 from both sides. 10x is equal to 120. And then, dividing both sides by 10, x is equal to 12. What's the question asking for? The measure of angle ABD. So we want to go through and find this 7x plus 4. Well, let's write that down. 7 times, we know x is now 12, plus 4. 7 times 12 is 84, plus 4, so we have 88 degrees. So this angle, angle ABD, is 88 degrees. If they had asked for angle CBD, we would plug in 12, have 36 plus 9, and have 45 for the other one. But notice these two angles together, they're not supplementary. They don't add up to 180. They add up to 133. Okay? Let's go on to 35. It says, tell whether angles 1 and 2 are vertical angles. Well, they're definitely not vertical angles. Are they adjacent angles? Why, yes. They are adjacent. They have a common ray and a common vertex. So those are definitely adjacent angles. Are they a linear pair? No, they don't form a line. Are they complementary? I don't know yet. So let's see if we can figure out what the sum of these two has to be. Well, notice we do have this 64 over here and the 36 over here on the left. The sum of these two angles, 36 and 64 is 100. Well, that means that the measure of angle 1 and the measure of angle 2 have got to be 180 minus 100, because an entire line is 180 degrees, which is 80. Well, that means that they can't be complementary, because complementary means a sum of 90. It's not supplementary, because supplementary means a sum of 180. So the only thing that angles 1 and 2 are in this case for 35 are adjacent. They have that common side and common vertex. Let's take a look at 36. Are angles 1 and 2 vertical angles? No. Are they adjacent angles? They do have a common vertex, but they don't have a common side, so they're not adjacent. Are they a linear pair? No, they don't add up to form a line. Are they complementary? Well, let's see what their sum is. Again, the two angles that are listed, 41 and 49, if we add them together, their sum is 90. Well, that means that the rest of these two, the measure of angle 1 plus the measure of angle 2, has also got to equal 90, because all four of these angles must add up to 180 degrees. Well, because their sum is 90, that means they are complementary. They're not supplementary, because their sum is not 180 degrees. So on 36, this is just complementary. Let's take a look at 37. Are they vertical angles? Well, yes, they are. They're on opposite sides of these two intersecting lines, and that's where we have vertical angles. So vertical angles checks. Are they adjacent angles? Well, no. If they're vertical, they can't be adjacent at the same time, so that one's out. Are they a linear pair? No, they don't form a line, so that one's out. Are they complementary? Well, let's see. Because this is a right angle here on the bottom, that means the lines are perpendicular, which means all of the angles here have to be 90 degrees. So the measure of angle 1 plus the measure of angle 2 is, well, that's 90 plus 90. That's equal to 180. Well, then it's not complementary. But it is supplementary. So angles 1 and 2, they are vertical and they are supplementary. Let's take a look at the next one. Number 38. Now 38 is tricky. It says, name two supplementary angles that are not a linear pair. Two supplementary angles that are not a linear pair. Well, that complicates things, because normally with a linear pair, I would take that angle and then I would come in with this angle. Well, those are a linear pair and they're supplementary, but I can't use that because it says not a linear pair. So let me take this one out and let's try something else. Notice on the diagram there are three angles marked as being congruent. This one, and this one. Well, what if we use one of these that has the exact same measure, this angle ACB? Well, now then, because it has the same measure as BCD, they have to be supplementary. So that's one pair of supplementary angles. Those are two supplementary angles, angle ACB and angle ECD. They do not form a linear pair, but they are supplementary. Their sum is 180 degrees. Look at 39. Name two vertical angles that are not complementary. Now let's think about this for a second. These two angles here and here, angle ACB and BCD, and also angle ECF, they're all congruent. But these two, ACB and BCD, well, see, the lines are perpendicular, so those two have to add up to another 90 degrees. That's another right angle. And so we can actually figure out that all of these angles that are marked here are 45 degrees. It says name two vertical angles that are not complementary. See, if I go with the easy vertical angles, which most people want to shoot for, angle ECF, this one in green, and angle ACB, see, these are definitely vertical angles, but they're complementary because their sum is 90. So I can't use those pairs of angles. I have to try something else. Well, there's not a whole lot of vertical angles here, but there is another pair. Take a look at this one, angle ECD. Well, I don't have one vertical with that. I got to try something else. Let's go to angle FCB. Angle FCB is part of two lines intersecting. And now then, look at this angle, angle ACE, and this angle, angle BCF. These two angles are vertical, and they are definitely not complementary because angle BCF by itself is already bigger than 90, right? So this is the only case that we can see from the diagram. This one is much trickier because it says not complementary. Let's take a look at number 40. Name three pairs of complementary angles. Well, as we mentioned before, all three of the angles that are marked have a measure of 45 degrees. 45. Well, so name three pairs of complementary angles. Angles ACB and angle BCD. All right? That angle right there, that is definitely complementary. Those are a pair of adjacent angles. And so their sum is 90. That's one pair. Let's take a look at another pair. How about angles ACB and angle ECF? Well, again, that's two angles here and here. They are complementary. They add up to 90. Well, then let's take the last pairs that we can look at, BCD and ECF. Again, both of them are 45 degrees, so they have to be complementary. Now then, are any of these vertical angles? Well, we do have vertical. If you look at these two angles, these are vertical. None of the others are. Adjacent angles. Well, we do have adjacent angles, and that comes from these two. They have a common side. That common side being ray CB. And then neither, well, the only one that's left is these two right here, and those are not vertical from each other. They are not adjacent. So these are the two that we have to say neither one of those two options. Remember, all three of these pairs of angles are complementary. Their sum is 90, but only one pair is vertical, only one pair is adjacent. Look at problems 41 through 44. It says, tell whether the figure is a polygon. If it is not, explain why. If it is, tell whether it is convex or concave. Well, let's take the two that are not polygons. Number 42 is not. Why not? Because of this segment right here that's going through. If we didn't have that, if that were not there, then we actually could say that this is a type of polygon because it does have all segments. But this goes in. It's actually two polygons put together. 42 is not. 43 is also not a polygon. And again, the reason why polygons are made up of segments, we have part of a circle here, this curve. And so this is the reason why this is not a polygon. So that leaves 41 and 44. 41 is made up only of segments. It doesn't have any segment going through connecting across, so it is a polygon. Now, is it concave or convex? Well, if we were to continue on this segment right here, it would go through and hit the other side of the polygon. So this is concave. It caves back in towards the middle, all right? And we don't study very much about concave other than that is a concave. Number 44 is convex. Why? Well, if you continue any of the sides, none of them go back in towards the center. They're all coming away. So this is a convex, and this is the one that we studied more in our work. Let's take a look at number 45. It says identify two different equilateral polygons. A polygon that's equilateral means it's all sides the same. Doesn't mean all the angles are the same. But we do want to have all the sides the same. So let's take a look at the easy one here in the middle. We call this a pentagon because it has 5 sides, and that looks to be like it's irregular. We don't know, but it does seem to be regular. But it definitely is equilateral. All right. So this is a pentagon, and that is equilateral. Can we find another polygon here that is equilateral? Well, we can if you look at the outline only of this star. Take a look at how many of these sides there are. Well, see, if you wanted to have this without the little segments connecting between, all right, without the pentagon that we just had, just the outline of that star in blue, that is a 10-sided polygon, and all the sides that I have in blue, they're all marked with that double hash, which means they're all congruent. This is a decagon, right? A decagon there. Now, there are other possibilities of side lengths that we could have. You could have a shape like this. This would be a quadrilateral. Notice it's not regular. Side lengths aren't all the same, so it's not equilateral, it's not equiangular, but it is a quadrilateral. That's one way of having a quadrilateral. A triangle. Well, there's a whole bunch of ways to have a triangle here. The little ones on the outside, like AKB, you could just break those off. But take a look at this triangle here. Triangle GKC. See, the base is GC, and this is also an isosceles triangle because sides GK and KC are congruent. They have the same length. So that's an isosceles triangle that we can look at, besides just the ones on the outside. If we were to look at this shape here, 1, 2, 3, 4. There's another quadrilateral, right? We can have a quadrilateral like this. So there's lots of ways of having different shapes with different side lengths, not necessarily congruent sides or angles, but we do have other polygons that are listed. These are some of the problems from the extra practice. Again, this is not sufficient review, but these do go through some of the main ideas of Chapter 2.